Hi, you can screen?
Yes,
And
sir.
am I audible? Right, fine. Okay. So what we did in the last time, in the last lecture, we have seen this recording, right? Ah, it is under recording. Fine. So in the last lecture, we have seen various types of proofs. That's mean how, if you have a statement and if you want to prove that statement, then how will you proceed, right? So there are some trivial proofs, vacuous proof, proof by contradiction, proof by contraposition, and also direct proof. So there are few more types of proofs, and we will go into the details today. Today we will see only one type of proof, that is the proof by mathematical induction. And in our next lecture, that will be the last lecture, we will discuss some more proofs and proof strategy, and that will be over of the this logic chapter. Okay. So today I start with that mathematical induction. So you already familiar to this, but still we will discuss this one because we will use some terms of logic. Okay. Okay. So let's start. So we start with principle of mathematical induction. So what is it? You have already uh, know already all of these things, right? So what is a mathematical induction? So we write that. So first of all, let Pn be a statement okay. So in right, I got disconnected again. Okay, fine. So let Pn be a statement involving n. Okay, then Pn is true for all natural number n if the following two condition holds. So what is the first condition? This is called basic step. That is this step. In this step, we will prove that P1 is true. Okay, and we have another condition too. It is called inductive step. And it says that Pk implies Pk plus 1 is true. That is, if Pk is true, then Pk plus 1 is true, and this is true for all n. Sorry, for all k belongs to natural numbers. Okay. Now, if these two condition holds, that is, one is basic step, another one is inductive step, then we say that, or we prove that actually Pn is true for all natural number n. Okay. Now there are some misunderstanding here. Here we are saying that Pk implies Pk plus 1. That's mean if Pk is true, then Pk plus 1 is true. But some students take it in some other way, that they feel that okay, it is for all k, so that's mean Pk is true for all k. Note that we are not saying that. We are not saying that Pk is true for all k. In fact, that is our claim, right? This is not our hypothesis. We are not claiming, we are not assuming that. We assume that if Pk is true, then Pk plus 1 is false. Sorry, true. It might happen that pk is false for some cases. That will not be happening because we will prove that pk is true for all n, for all k. Okay. So here we are just saying that if, remember the statement if pk is true, then pk plus 1 is true. Fine. So we are not claiming here that pk is, or we are not assuming here pk is true for all k. Fine. In fact, it is our claim that Pn is true for all n. So this is one. Now, how to write this statement in terms of rule of inference, right? So we can say that. So in terms of rules of inference. In the last time we have seen some rules of inference, right? That's mean something, some statement or some propositions can be expressed in terms of logic operators only. Okay. So this, it can be expressed as, so P1, right? P1 is true, and for all k, Pk implies Pk plus 1, right? Then this 2 will imply for all n Pn. Okay. So in terms of rules of inference, we have this. That's mean that the principle of mathematical induction can be represented or can be expressed by this. Fine. Okay. Right. Now, there is another observation. Note that here we have written here basic step is P1 is true. Okay. So this is actually the standard principle of mathematical induction, but we can do some refinement as well. It might happen that that basic step, okay, is not starting from 1. It might happen that some basic step is starting from, say, some integer 2 or some integer from some positive integer from 3, right? It might happen. In that case, we will prove that basic step for p for n equal to, say, 2 or n equal to 3. In fact, it is not necessary that you have to deal with the natural number. Okay, so you can include some negative integers as well. So that's mean it might happen that your mathematical induction, that is the basic step, starting from, say, -5, -4, -3, and then goes to infinity. It might happen. That's when we are shifting all the integers into some left side. That's when from the -5. It might happen. So it will depending on the problems. Suppose if you are asked to solve a problems, then it might happen. And there is another part is that it might happen that for the basic step, you have to do 2 or 3 steps. For an example, you may need to check P1, P2, P3, these 3, and then you can start from the inductive step. So it also might happen. It may not be true that only if you start with P1 and then start with some Pk, then it will work. It may not work. So in that case, for the basic step, you might need to check P1, P2, P3. So we will see some examples in that type, right? But this is the standard part or standard version of principle of mathematical induction. So any confusion? I am confusing you. Okay, fine. I think it is clear, right? You already know this one. Okay. So first of all, today we will see that proof of this mathematical induction. So in other words, if you are a mathematics student, now you can simply first of all say that, okay, no, you cannot prove the principle of mathematical induction. You can say that. Okay. If you state that, okay, mathematical induction cannot be proved, then also you are right. Right, actually it cannot be proved because it is treated as an axiom. But actually this axiom, we generally do not assume this as an axiom. Okay, so this mathematical induction is equivalent to something else, and that is actually we assumed as axiom, and that axiom is the Weyl ordering principle. Do you know what is a Weyl ordering principle? So during the calculus course, actually I have done this to my batch. So do you know? Do you remember if there is any student from group D? Remember? Do you know what is a Weyl ordering principle? Yes or no? If it is no, it is also fine. I do not expect that you remember all of this stuff.
I remember only the term, but not exactly what it means.
Good, good. Yeah, you should speak out, right? So whatever it is, there is nothing wrong if you don't remember something. Also, if you ask me some rules or something, also I also forget many stuff. But now I know all of this stuff because I have to teach and I have read these parts. Otherwise, I also forgot so many parts. So that is completely fine. Okay, I have to new. Fine. Okay. Now start with that Weyl ordering principle. Now this is an axiom. Do you know what is an axiom? So that's mean you cannot prove this, or you can say in some good language. So mathematics starting from here only. So there are some axioms in mathematics. That's mean so mathematics starting from that. So you cannot prove it, but these are as an axiom. Okay, and you can prove all the other stuffs using these axioms. Okay, so axioms means it is true, and we assume that this is true, and then this is the starting point of mathematics, and then after that, after assuming all of this, that mathematics can proceeds only. Okay. Okay. Now this says that every non-empty subset S of the natural number of the set of natural numbers, we call this is N. You also know that. Okay, has a list element. Has a list element.
It has a supremum or infimum like that.
Sorry.
That means every non-empty subset of natural number has a supremum infimum like that.
Oh no, not supremum infimum. It is not super. It is a list element, and obviously it does not have any supremum, right? For an example, if you take say 2, 3, 4, 5, 6 and goes away, then it is also a subset, non-empty subset, right? Starting from 2 and goes up to infinity, but
It
it
has
does not have.
infimum.
Right, it has infimum, but we will not use the term infimum because generally there is a different. Okay, that is we will come to that when when I teach you that set theory. Then I will come to that part, that what is a supremum and what is an infimum. But supremum and infimum may not be belong to that set. For an example, you have open interval 2, 3, and if what is the supremum 3, and what is the infimum 2, right? But this Okay, so 2 is not in that set, right? But if you call about the least element, that set does not have any least element, but it has a infimum, that is 2, and 2 is not in that set. So therefore infimum and the least element both are actually different. Least element means, okay, I will define here. Least element means the least element of that set, and infimum means the greatest lower bound. Okay, so both are different actually. So I will define here what is the least element. As a least element, that is, there is an integer, say m belongs to S such that m less than equal to n for all n belongs to S. Okay, so S has many elements and this is the least element. So that's mean if you take any other elements from S, then that element should be bigger or equal to than m. Okay, so this is a definition of least element. So least element and infimum both are different. Okay, so now if we assume this as an axiom, then, and this is axiom actually, so if we assume this, then we can prove inductive that the principle of mathematical induction. In fact, you can prove that Euler ordering principle and principle of mathematical induction both are equivalent. So in that sense, you can say that if this is an axiom, so this is also an axiom actually, because they are actually equivalent statement. So Euler ordering principle and the principle of mathematical induction both are equivalent. Okay. So therefore, if you treat the Euler ordering principle as an axiom, then you can prove principle of mathematical induction. In other way, if you assume principle of mathematical induction as an axiom, then you can prove the Euler ordering principle. But in general, people assume this Euler ordering principle as an axiom and prove the principle of mathematical induction. Okay, so here we will see proof of the both side. So Euler ordering principle implies mathematical induction, and the mathematical induction implies the Euler ordering principle. We will see both. Okay. Now before going to that proof, we have another term called strong induction. So strong induction means it is just a strong version of mathematical induction. Strong version in the sense that not strong actually, it is something called actually a weaker version, because we are assuming something stronger than that. I don't know why the name is strong induction. But anyway, so here we need some strong hypothesis, you can say. But the statement is actually weaker than. Okay. But principle of mathematical induction and the strong induction both are again equivalent, because you can prove that both are equivalent to the Euler ordering principle. So okay, now first define, so what is that strong induction. Now again, so let Pn be a statement involving n. Now then Pn is true for all natural number n if, again, if the following two condition holds. So first one is P1 is true, okay, and second one is if P1, P2 up to Pk are true, then pk plus 1 is true. And this is for all natural number k. Okay? See, that hypothesis is little bit stronger here. That's mean we are assuming that P1 is true, and we are assuming that P1, P2, P3 up to Pk all are true. If all are true, then Pk plus 1 is true. Okay? And if these two condition holds, then we say that Pn is true for all n. And this is called strong induction. Though the actually that result is little bit weaker than the mathematical induction, because here we need some strong hypothesis. But why still it says that strong induction? Because it is more useful. For an example, if you have some problem, if you want to solve some problem, that problem might be solved by using strong induction, but not using mathematical induction. That is the reason it is called that strong induction. But if you look at that version, this is little bit weaker. Okay, so we should not go into that part, which is weaker, which is strong. So that's it. That is a strong induction. Right now, we see the proof.
Sir,
Yeah.
so if the domain contains, let's say, like what we have talked before, like in the induction part, like it contains some intervals. So in that case, it is not possible for us to prove for each and every point, like from
Huh.
one to, like from that, let's say the interval is closed, open A to open B, then
Huh.
it is not possible for us to uh, prove at each of the point between A and B and up to what we assume.
Right, right. Huh.
So in that condition, what should we do?
No, but that mathematical induction and or strong induction both are true only for the natural number.
Okay, but you have told, right, there should be a case like there should not be natural numbers. There should be some points.
No, no, no. I am not saying that. I am saying that it is not necessarily the natural number. In fact, it can be, you can shift that natural number a little bit. For an example, your domain can be this, say -5, -4, -3, -2, -1, 0, 1, 2, in that way. It can be
It
your domain.
it would be integer, right?
Right.
Okay, sir.
It should be an integer. I am just saying that, see, this is also behaves as natural number, right? We are just shifting the natural number in the left side up to 5. That's all.
Okay, sir.
So though I am stating here that strong induction or mathematical induction both are true for all natural number, but it might be useful for some integers as well, which is a superset of natural number. For an example, this is a superset of natural number, but still you can use mathematical induction to prove this kind of statement, this kind of domain.
Okay,
Sir,
Yeah.
sir, if my P of n is like, matlab, n is greater than n square minus 9. P of n is greater than
Acha, n is greater than
n square
n
minus
square.
9.
Huh.
So sir, here P of 1 is true, P of 2 is true, P of 3 is also true, but P of 4 is false.
Huh.
So sir, matlab, from strong induction I should say na, matlab, I can say that P of 4 must be true.
Why?
Because P of 1, 2 and 3 all are true.
No, no. What is the statement? You can see that if P1, P2, P3 are true, then P4 is true. But
Hmm.
here P1, P2, P3 is true, but P4 is not true. That's when you
Haan.
cannot use the induction. Yeah, you cannot use the induction. This is the condition. This is the condition. This is not the conclusion. This is the hypothesis.
Okay, okay. Sorry. I was
Okay.
confused. Okay,
And
okay,
this
sure.
is the conclusion.
Okay, okay.
Okay.
Yes, sir. Yes, sir.
Yeah. And thank you for asking, because you should ask. Even that is a simple question, still you should ask. Okay. Also, I also get some energy if you ask something. Okay. So first we prove principle of mathematical induction implies Euler-Ordering property of n. Okay. So this. So we assume that Euler-Ordering principle, we assume that principle of mathematical induction, and we prove that Euler-Ordering property of n. So actually, we want to prove that. Now again, you can see, so how will you proceed? Now you can say that let P be the statement that n has the Euler-Ordering property. Okay. So we assume that this one P is the statement that n has the Euler-Ordering property. Then what is my negation of P? That's mean n does not have the Euler-Ordering property. Okay. Now what we'll prove actually? So we prove that negation of P implies a contradiction. Okay. We this. Oh, this is end. So we prove this one. So negation of P is gives a contradiction. So that's mean your P is true, right? So this will be proved by contradiction. Fine. Now, what do you mean by n does not have the Euler-Ordering property? So that's mean so assume minus P is true. Then and what we can say that there exists a non-empty set S, or say subset of natural number such that S does not have any least element, right? Now what does it mean? So that implies 1 does not belong to S. Why? As 1 is the least element of n. Okay. So because if 1 belongs to S, then 1 should be the least element of S. But here we are assuming that S does not have any least element. So therefore 1 does not belong to S. Fine. Now we consider a new set T equal to n minus S. Now since that's mean what is n? N is T union S, right? So S and T both are complement to each other. okay, in the set of natural number. So now since 1 not belong to S, so therefore 1 belongs to T. Okay. Now let 1, 2, 3 up to M belongs to T for some M belongs to natural number, or you can say N bigger or equal to 1. Okay. So we had 1 belongs to T. So we first assume that 1, 2, 3 up to M bigger or equal to 1. So M can be 1 as well, right? Or you can say here N, it looks good. Okay. Now if that N should be no N T. If T does not contain N plus 1, what does it mean? Contain N plus 1. So that's mean N plus 1 is in S and that is the least element, because the previous all the element belong to T only, right? Now if T does not contain this, then N plus 1 is the least element of S, and this is a contradiction. Now what contradiction it is? Can you tell me what is the contradiction here? So this is a contradiction, means R and minus R, and R, what is R?
Sir, R is S does not have any least element, and then we are
Right,
used that minus R is that S has a least element.
right. So we have this contradiction, right? Okay. So therefore,
Sir, in this case where we use PMI to prove
sorry,
it's simple
ha,
contradiction, we simply use by contradiction. No, it is not by PMI, right?
no, I did not get what.
And this is proved by contradiction. It is not proved by PMI, right?
No, no, it is a proof by contradiction, right? Now, still now we get a contradiction. Fine.
Sir,
Huh.
sir, when you said that 1 does not belong to S and S does not have a list element, so doesn't it also imply that 2 also does not belong to S? So similarly, any natural number cannot belong to S by induction, so S will be an empty set. So that is also another contradiction.
Okay, okay, okay. I got it. So there is a confusion here. So we did not prove it. So we have not proved it. So just we get a contradiction. Okay, right, right. I got you. So I should not start with that. Just a minute. Since I start with that,
Excuse me, sir. Sir, we can only comment on the presence of 1 in T. Sir, how are we so sure about 2, 3 and others?
no, no, no. We are
Sir,
not
we can
saying that. We are just saying that it is up to n, where n is just bigger equal to 1.
sir we can prove that S will be an empty set, and initially we assume that S is non-empty, so that will become a
Right,
contradiction.
right, right. So we should not start with this one. No, no, that is fine. So I actually wanted to prove in that way, but here I use this one. Now I want to justify myself.
So we
So
can continue
that
from
was
now here only too, right? Like
right.
we afterwards we can say that since this is a contradiction, that means T has to contain n plus 1, because just the last line we said if T does not contain n plus 1, then n plus 1 is the least element. So we can say that if T we assume that T contains 1 to n, and this implies that T has to contain n plus 1 also. Then using the principle of mathematical induction, we can say uh, that T contains every element of
Right,
n.
right, right. Got you. Got it. Right. Fine. Right. Now this is a contradiction. Now when we get the contradiction, if T does not contain n plus 1, right? T this contradiction. So that's mean that n plus 1 belongs to T only, right? Fine. Now if you look at the statement that, see here, 1
Sir, we have assumed like S is a non-empty subset. So in from this
no.
induction part, we can prove that all the elements belongs to and S is an empty subset. And this
See,
also
that is
comes.
fine. That is fine. The problem is that I start with this one. So one part is, see, I'm saying you, if we do not assume this one, then what is the one proof? You just first assume that assume that S is non-empty. Okay, and then here you get that n plus 1 belongs to T. Then by the principle of mathematical induction, you can say that all the natural number belongs to S. Sorry, belongs to right S. So therefore again S is not empty. And we assume that S is non-empty, so that was a contradiction. So we are done. So we are doing that one only. So that is fine. Okay. Now what is, now again I am getting confused here. I am using principle of mathematical induction, right? But
Yes, sir, using principle of mathematical induction only. The second, we said that P1 is true because 1 does not belong to S, that means 1 belongs to T. That is our basic condition. And assuming Pn is true, Pn plus 1 is also true. If P is the statement that n belongs to T.
right, but I'm now confused about that. We are using principle of induction or strong induction here?
Strong induction actually, but it's more or less just the same. Uh, because we assume n to be greater than or equal to 1. So we can just say that
Ah,
for k only.
okay. So here 1 belongs to T and n belongs to T imply
N plus 1 belongs to
n
T.
plus 1
So
belongs to T, right. So that's by the principle of mathematical induction. Mathematical induction. All the natural number belongs to T. So therefore n subset of T. Now that implies S is empty. Now again this is a contradiction. Contradiction, again you can have this contradiction actually. So R and minus R, where R is a statement that S is non-empty. So that's all. So therefore we finally get a contradiction and we assume that Euler-Lorentz principle is not true. So minus P implies the contradiction. So therefore n has the Euler-Ring principle.
Sir, we cannot say it by PMI, we can say by strong induction the last statements. Because if n belongs to T, then we can't say n plus 1 belongs to T, because something between 1 and n can belongs to T, belongs to S. So we should say that if 1, 2, 3 up to n does not belongs to T, then we can say that there is no least element should be n plus 1. But for n
Yeah, I
belongs to
am
T,
also confused a little bit here. So that's why
Sir, but we
uh,
let's say we replace n with k. So we are saying that for some k greater than equal to 1. Let's start with k equal to 1. That means if 1 belongs to t, that means 2 belongs to t. Then if 2 belongs to t, for k equal to 2, 2 belongs to t. Since we already proved that 2 belongs to t, then we can say that 3 belongs to t.
that is actually what is the statement that actually what you can do, that as I told you, that principle of mathematical induction and the strong induction both are same actually. So first of all, this condition, since this is true, from 1 to 2 you can prove, 2 to 3 you can prove, and then up to n you can easily prove, right?
Yes, sir.
Yeah, you are saying that one only. So 1 to 2, 2 to 3, and that up to n you can prove, and then you can say that by, if you want to say that strong induction, then it is fine. You don't need that actually.
Sir,
Yes.
Sir, one more question. Sir, is strong induction and induction, which is more strong? Like the strong induction part is more strong.
Right. In the sense that there are some problems where you cannot use directly mathematical induction, but you can prove by strong induction. So in that sense, the strong induction more strong.
Yes.
Right.
Sir,
But that problem can be proved by the mathematical induction as well, but you need to give some extra argument. That's it. For an example, just he gave that argument, right? So 1 implies 2, 2 implies 3, 3 implies 4, up to n, and then you can apply the strong induction in that way.
sir, like the example, one of us have raised n is greater than n square minus 9. In that example, like 1, 2, and 3 are true.
Right.
But if we go for other cases like 4, 5, and then
But 3 does not imply 4.
yes, sir. Okay, I understand.
You can say that 3 does not imply 4 for the mathematical induction, and for the strong induction you can say that 1, 2, 3 does not imply 4. That's all.
Okay, sir.
So therefore you cannot use induction there.
Okay, sir.
Okay.
So what does line means? R intersection, R and negation of R. Why we write this? We can simply write this is a contradiction. What is the meaning of writing this? R and negation of R.
This one,
Yes, sir.
to understand what is the contradiction.
So the contradiction is that we assume that S is non-empty, but here we are proving that S is empty set.
Right. So that is a contradiction, right? To understand the contradiction, we are writing this one.
I cannot understand this one.
So what is a contradiction, first of all? Contradiction means you need a proposition R such that that statement will imply R and minus R both. So that is a meaning of contradiction. Okay?
Little bit.
Right. See, first listen. So what do you mean by a contradiction? Contradiction means you need a proposition R, right, such that R and negation of R both are true. Okay, so here this is the contradiction, means here R is my S not equal to empty, so non-empty set, and then actually what is get? So if you take minus P is true, then we get S is empty, sorry, S is non-empty, and again we are getting S is empty. So that's when minus P implies R and minus R both. So therefore this is a contradiction. It is fine if you don't write this one. I am not, that is the reason that I am writing here, it is a different colors. So that's mean you do not write, no need to write this one. But to understand the contradiction in terms of logic, I am writing this. In general, in a proof, you do not write this, right? But here I have written this one for the logic part only. Okay. Okay. So we get a contradiction. Thus, we can say that.
Sir,
Huh.
am I audible?
Yes.
Yes. Sir, can you scroll up little bit at the first statement, P and negation of P?
1 minute. Right. Yeah.
Sir, here, sir, is it the question is what we wanted to prove that N is a well-ordered set?
Huh. N has the Eulerian principle, right? Yeah.
Sir, I don't understand one thing. Let if we take P as a set of even numbers,
P is a
like
set of
T
even
as
numbers.
T, let we say that S is a set of even number, and so T will become a set of odd numbers.
Right.
So in both cases, we have a least element. So how we are saying that in the last statement that we have one से लेके n तक element है, so n plus 1 will also be there.
But that's the second part. Now, we first proved that if T does not contain n plus 1, then that cannot be the case. We proved that first. The first contradiction we arrived at. Because for 1 belongs to T, if we assume that 2 does not belong to T, then 2 is the least element of S. We arrived that contradiction first.
See, here I am writing 2, 3 up to n, that is fine, but that does not mean that 2 is always exist. That is the reason I have written here, na, n be bigger equal to 1. That n can be 1 as well.
Yeah. Okay.
Right. But anyway, but still I think I need little bit precise on mathematical induction only. So I have to be precise here, I think a little bit. So I will look into this part. So this is fine. I know this is fine. But the problem is that I think I need to write maybe one extra line. Because it looks like here from this, I am using strong induction. But there will be not a problem because strong induction and mathematical should not be a problem. Okay, anyway, so I will look into that and then I will send you. Then definitely there will be not a problem on this part. That is easy. Now we can look in the other part. That is the main part which we need to prove. Because actually why we are here, we want to prove the mathematical induction by assuming the Euler-Ring principle, right? Because in general, people assume Euler-Ring principle as an axiom. So that's when this part actually, for fun, we don't need that actually. It is only for showing that both are equivalent. That's all. But we actually don't need that because in general, people assume this one, that is that Euler-Ring principle as an axiom. So you don't need to prove that. And then you prove the mathematical induction by the Euler-Ring principle of N. So now this is the main part. So Euler-Ring principle of N implies the principle of mathematical induction. Okay. So we assume that part and we will prove that part. So first of all, let Pn be the statement, not be the statement, be a statement involving n. Okay, involving n such that we need these two conditions now. First of all, P1 is true and this is if Pk is true, then Pk plus 1 is true for all k. Okay, so we have these two conditions. Now then we wish to prove that, write a different pen, we wish to prove that Pn is true for all n. Okay, we don't know that, we want to prove that. Now let S be the subset of set of natural number n such that Pn is false. Pn is not true. Okay, so that implies directly 1 does not belong to S. Why? As P1 is true. Okay, fine. Now, if possible, assume that S is non-empty. Okay. Now we assume that S is non-empty. Now, if we assume that S is non-empty, and then by the Euler-Lorentz principle, S has a least element. Now then, by the Euler-Lorentz principle, S has a least element say k plus 1, where k is bigger or equal to 1. Right? Because k cannot be 0 because 1 does not belongs to S. So therefore, if S has a least element, that least element should be bigger than 1 or bigger or equal to 2. Okay? So this. Fine. Right. Now since k plus 1 is the least element, so that implies k does not belong to S, right? So that implies Pk is true, right? Now if Pk is true, look at the condition. Okay. Now we say that, and this is true for all k. Now that implies so by property 2, Pk plus 1 is also true. So that implies k plus 1 does not in S. Because we assume that a collection of natural number where natural number n where Pn is not true. But here Pk plus 1 is true. Therefore, k plus 1 is not in S. Now this is a contradiction. Now again, can you tell me what is my R here?
K plus 1 belong to S.
P of k plus 1 is true.
What is my right? No, it is just k plus 1 belongs to S. Okay, so this is a contradiction. Now, why we get this question? We assume that PS is non-empty and we get a contradiction. Okay, so these were our assumption and we get a contradiction. So therefore, this assumption is not true. So thus S must be empty. So that implies Pn is true for all n. For all, we can say that natural number n. Now this proves the principle of mathematical induction.
Sir,
Ah,
here we are assuming that if Pk is true, then P of k plus 1 is true, or we have to prove. But in normal cases where we solve the problem, we assume that Pk is true and then we prove that Pk plus 1 is true. If Pk plus 1 is true, then P of n is true for all n.
it is not clear. Actually, your voice is too much noisy.
Now, is it clear now?
Okay, you say what you are saying?
So here we are assuming that if P of k is true, then P of k plus 1 is also true. But in normal cases where we solve the question of normal induction of the mathematical induction, what we assume that suppose P of k is true, then there we prove that P of k plus 1 is also true, and here we are assuming that P of k plus 1 is true.
Right.
Sir, your voice is breaking. There is some network issue, I guess.
See. Huh. Actually prove that in the mathematical, what is the actual statement? Mathematical statement, the statement of not. Okay, now it is fine. Hello. Hello.
Yes, sir, your voice is clear now.
What is actually the principle of mathematical induction? It means, so when we can apply, so if P1 is true and if Pk is true implies that Pk plus 1 is also true, then we proved or then we can say that it's true for all n. Okay, so that's why this 2 is our assumption, and then we prove that. Okay, so these two are assumption and this is, or you can say hypothesis, and this is my conclusion. Now here we are using, here we are proving the principle of mathematical induction, right? So we are not using the principle of mathematical induction. We are proving that. So therefore, and this true, and then proving that this is true. Okay. Now, when we solve a problem, then we have to prove that this is true, this true, and this true, and then we can say that Pn is true. And in that case, we check. We are not assuming that P1 is true. We check P1 is true, and then also we check this one. So that's when if Pk is true, then we prove that Pk plus 1 is true. That's when we need to prove this, and then only we can say that Pn is true for all n. Did you get the point? But here we are proving that mathematical induction. Therefore, we have to assume this, and then only we can prove this. Is that clear?
Yes, sir.
Right. So this is the difference only. Okay. So here we are assuming P1 is true, and we are assuming that this statement is also true, and then we are proving that Pn is true. And when we solve a problem, there that P1 is true, and we prove that this one is true, and then we say that since these two statements are true, so therefore we, by mathematical induction, we can say that Pn is true for all n. This is the difference. So the question is, we will prove that all horses are of same color. Okay, so we will prove that. So we will prove by mathematical induction. Now this, let Pn be the statement. So any n horses are the same color. We can see directly back. Okay, so this is my statement. Now you can see that P1 base step. Now P1 is true as any singleton set, singleton, any single horse has same color. So there is nothing to prove here, right? So trivially this is true. Now inductive step. So assume Pk is true. So that is any k horses are the same color. Now we need to prove that any k plus 1 horses are the same color. Now assume, take k plus 1 horses. Say h1, h2 up to hk plus 1. Okay. Now by the hypothesis or by assumption, that h1, h2 up to hk, this one we have K set, K element, right? Have same color. And H2, H3 up to Hk plus 1. Again, this is a K element. Again, have same color. And H2, H3 up to Hk minus 1, sorry, Hk are in common. Right? So that's H1, H2 up to Hk plus 1 are the same color. Right? So that implies Pk plus 1 is true. So any K plus 1 are the same color. So thus by principle of mathematical induction, we say any horses, or you can say that all horses same color. See, so that's when we prove that if you take any collection of horse, then there are many brown, right? There are many different colors horse. Then what is the wrong in that statement? Now you can give the answer.
Sir, sir, the inductive chain is broken because P2 is not true.
Right.
P1 does not imply.
So what exactly are we proving?
So all horses are the same color.
But what we actually proved that this thing, given any integer n, we can have a set of n horses of same color.
Right.
That's not the same.
Right. So that's mean all the horses are the same color.
Sir, we just proved that given any finite integer, we can have a set of finite n horses of same color.
No, we are not saying that.
No, but that's what we proved.
No, we did not prove that. You just see the statement of the mathematical induction. That is true for all n.
Wait. So can you show the statement again?
Sir, here P1 does not imply P2.
No, I got the answer. Just let me clarify, Akshay. Yeah, this is a statement that all horses are the same colors. Okay, and we have taken that Pn. Any n horses are the same color.
Pn I didn't understand properly.
Right, and then this is true for all n. So therefore, all have same color. See here, basic step that P1 is true, and also if Pk is true, then Pk plus 1 is true. But here we use one fact: these are in common. So that's mean here it is clear that P1 is true. It is clear, and it is also clear that Pk implies Pk plus 1 is true for all k bigger equal to 2. The only problem is that P1 does not imply P2. Or better to write, P1 implies P2. That does not true. So which argument we have given this one, that is not true, because if we have 2, that is k equal to k plus 1 equal to 2, then we have H1 have same color, only singleton set, and also H2 that singleton have the same color, but they do not have any common element. So therefore, so this set is actually empty. So therefore, we cannot say that H1 and H2 have the same color. So this is the problem. But here P1 is true and Pk implies Pk plus 1. This is also true for all k bigger or equal to 2. Only this part is not true. So therefore, we cannot use actually mathematical induction. So that is the wrong statement. Okay, is that clear to everyone? Okay, I think I am audible, right?
Yes, sir.
Okay, fine.
Sir, here if k is less than 2 or less than or equal to 2, or I should say if here k is equal to 2, then p of 1 doesn't imply p of 2 because because they don't have any common element. So
No, I'm right.
So we are telling this,
Right.
and for this very reason we are telling that we can't apply mathematical induction to prove this.
Right.
Okay, sir.
So that's mean here I have given one argument, but that argument is wrong. Wrong here. So here I am proving that Pk is true. Pk implies Pk plus 1 for all k, but that is not true. Here actually I prove Pk implies Pk plus 1 for k bigger or equal to 2. For P1 implies P2, I did not prove that. So
Yes.
therefore, the argument is not complete.
Okay.
Okay. Now there are some common problem which you generally face, and you already have seen this kind of problems. For an example, by using mathematical induction, you can prove that. So 2 into 7 to the power n plus 3 into 5 to the power n minus 5 is divisible by 24 for all n belongs to natural number. Okay, so you have seen this kind of problem, right? So how to proceed? So we first take the statement, let Pn be the statement that this one, that 2 into 7 to the power n plus 3 into 5 to the power n minus 5 is divisible by 24. This is the statement. Now, base step. So take n equal to 1. Then what is this? Then that will be 2 into 7 plus 3 into 5 minus 5. So it is 24. So therefore, P1 is true because this is divisible by 24 for n equal to 1. So base step is fine. Now inductive step. Now let Pk be true. Okay, so that is 2 into 7 to the power k plus 3 into 5 to the power k minus 5 is divisible by 24. So therefore we assume this equal to say 24 p. Okay, so for some integer p. Now we need to prove that pk plus 1 is true. So we need to prove that this plus 3 into 5k plus 1 minus 5. We need to prove that this is divisible by 24, right? Now we have to just manipulate this one. So we first take 7 common, then it will be 2, 7 to the power k. Forcefully we can take plus 3 into 5 to the power k minus 5 and then minus 3 5 to the power k plus 5. We can write this one in this way and then plus 3 into 5 to the power k plus 1 minus 5. Now this part we already know it is 24p. So it is 7 into 24p minus 21 5 power k plus 35 plus you can write it is 15 into 5 power k minus 5. So it is 7 into 24p minus 6 5k plus 30. Not 65, it is 6 into 5 power k. 24p minus, if you take 6 common, then it will be 5 power k minus 5. Right. Now, how can you say that this is divisible by 24? So that's when it is sufficient to prove that this is divisible by 4. If we can prove that, then we are done. Now, how can you prove that this is divisible by 4? Can you say any quick argument? Can you give any quick argument for this?
We can apply.
Huh?
Yes, so sum GP.
Sir, we'll write 5 as 1 plus 4 whole ka power k and then we'll apply that binomial.
Right. So that is, I think, good approach. So 1 plus 4 power k and then it will be 1 plus k choose 1, 4 plus k choose 2, 4 square up to k choose k 4 power k minus 5. And then this will be divisible by 4. So you can write it as a 4 cube. So therefore, pk plus 1 is true. So thus by principle of mathematical induction, we can say that Pn is true for all n. So we are done. Okay. So it is already time. So I think we can stop today. So any quick question?